Today, I'm going to introduce what we call the t-distribution. Now, the first thing we have to kind of think about, number one, the t-distribution is about quantitative data, which means that in the past, we've talked about the true proportion. We used p hat for our statistic, for our sample. We used p for our population. Okay, we're not going to do that. You are going to be very tempted to say, I'm 95% confident that the true proportion of, but that's going to be wrong. You're going to have to be careful, right? Now we're going to be talking about the true mean, right? The true average result. And so we're going to be using X bar instead of p hat. We're going to be using mu instead of p. So our symbols change, right? So in the null hypothesis, it's going to be mu equals, not p equals, or mu is not equal to or greater than or less than for the alternative, right? So the first thing we have to kind of keep in mind is that we're going to be talking about an average, a mean. So the vocabulary that you're going to be seeing written into the question, it's going to be talking about the mean of whatever instead of the proportion, which also means that we will no longer have success and failure. We don't have X. We have an actual average that comes out. And you're going to have quantitative data. Which also means that we're going to be using a different test statistic. In this case, when we're talking about proportions, we're using the z-distribution. So we use z-scores. In this one, we are going to be using a t-score. Okay? The t-score, well, the t-distribution was created because we actually don't know the population standard deviation in most cases. So the z-distribution requires you to at least have a pretty solid estimate of what the actual standard deviation of the population is. And in categorical data, we can do that because that's based on p. But in quantitative data, it's based on the standard deviation of the population. And I don't know this. And most of the time, I'm not going to know this. So we're going to be using a t-score. This t-score is what we're going to call the test statistic. It's exactly like a z-score. Does that make sense? If you look at the bottom of the fraction here, the s over the square root of n, last time you saw this, it was sigma over the square root of n, which is the official standard deviation of the sampling distribution, right? And we had that formula on the board. SD of x bar equals sigma over the square root of n. It's the same formula, but instead of using sigma, we're using s, right? Sigma, the little O with the tail on it, is the standard deviation of the population. S represents the sample standard deviation. S is a statistic. S goes with x bar, right? So this is your symbol for standard deviation of your sample. X bar is the symbol for the standard deviation of your sample, or the mean of your sample. Just like mu is the mean of the population, sigma is the standard deviation of the population. So these two things represent the same idea, the average. S and sigma is not written, but they mean the same thing as well. And of course, n is just your sample size. T still represents the number of standard errors away from the mean something is. It's a lot. Remember, standard error is equivalent to the standard deviation of the sample. But that's not exact because we don't know everything about the sample. And so we have to worry about that. Any questions about the t-score? A couple of other formulas that we're going to get into. Okay, here you have a few of our new formulas. This is your confidence interval formula. X bar plus or minus t star times s over the square root of n. I'll explain that in a minute. That's called degree of freedom. That's the next formula. This is exactly the same confidence interval formula as you had last time. It's your point estimate plus or minus the margin of error. It's exactly as it was before, except this time my point estimate was p hat last time, the proportion of my sample, but now we have the actual average, like literal add up my numbers, divide by the number of things I have, and you've got your average, okay? So this brings back a lot of things we haven't done in a while. This brings back one variable statistics, where if I need the mean and the standard deviation of a group, I can get it. That's actually not how it's going to work most of the time. You're going to have a data set, and in your quantitative tests or intervals, you have the option of using a data set or statistics. And we'll go over that in a minute. Okay. Okay, so this t star is represented by n minus 1. What that means is you have n minus 1 degrees of freedom. I'm not going to get too deep into degrees of freedom because I don't really need to know what that really means. What this means is that the z-curve is perfect. There's only one of them. All right, you tell me the mean and the standard deviation, boom, there it is. With the t-curve, you can tell me the mean, you can tell me the standard deviation, but there's an infinite number of curves for that mean and that standard deviation. Depending on your sample size, right, your degree of freedom exists. The smaller your sample size is, the wider the curve is. The larger your sample size gets, the closer and closer it gets to that perfect z-curve. So bottom line, when I'm using z and t, z is perfect. T is imperfect. It's got error built into it because I don't know everything about the data set. So it's got extra error built in, and it allows me to make estimations using incomplete data, which is usually how that works with quantitative sets. Okay, I'll get into that a little bit more in just a second about the curves. And at the bottom, I'm just kind of emphasizing that margin of error, that's the second half of your confidence interval formula up top. That's still what we call margin of error, right? And so the format has changed slightly from last chapter, but it's still your critical t-score. And last time, how we found the z-score, if I said 95%, it was always a single value. It's not true anymore. With the t-curves, the degree of freedom matters, right? And we'll look at your chart here in a minute. Degree of freedom changes the curve. And with the z-score, I didn't have to worry about that because I assumed that I knew the standard deviation. In this case, when I go to look up a critical value for a t-score or for a confidence interval, I'll have to take into consideration the actual sample size and the confidence level. And where those two things match up, that'll be your confidence level or your critical t-score. We'll look at that in a minute. To emphasize the curves that we're talking about, if you kind of imagine the z distribution, it's this perfect curve, and you know the exact spread, you know where it falls, and really the difference between z and t is all about spread, right? The wider the curve is, the fatter the tails are, the more error you have, right? The wider it gets. And so if I had let's say the red curve, I need to write that back in. I erased it. Here you have, this is your T curve with 10 degrees of freedom, right? So you have a very wide curve with a small sample size, lots of error built into the tails. So if I find a probability, I'd have a pretty high probability in that case. But if I increase my sample size, right, you know that as you increase sample size, that spread shrinks. Mean stays the same, but spread shrinks. So as you increase your sample size from 10 to 20 to 50 to 100 to 500, that curve gets narrower and narrower. And what it does is it gets closer and closer to that perfect Z curve, right? And so eventually when you get to, say, 300 or 400 of a sample size, if you did the probability using a z-score or a t-score, they're almost going to be the exact same values. Okay? So when sample sizes are large enough, doesn't matter which one I use. The sample size is large enough for me to have very little error built into it. So t-scores approximate z-scores, right? T-scores approximate z-scores. If you allow your t-score to go up, your sample size to go up, your t-score gets closer and closer to that perfect z-score value. For example, if I'm using 95% confidence, as I let my sample size go up, my t-score will start at like 1.8, then it'll be 1.9, then it'll be 1.93, 1.94, 1.95. Eventually it gets to 1.96. And no matter how much larger you make that sample size, it's just going to stay at 1.96 because that's its kind of perfect value. Little to no error at all. Okay. Let's look at the new stuff in the calculator. Little overwhelming here. Okay. We have a lot. Now, I'm not numbering these. These are the numbers that they are in the calculator, right? 1, 2, 3, 4, 7, 8, 9, 10, and then you have TCDF and inverse T inside your distribution menu. Let me distinguish between these, okay? Number one, the z-test, the z-interval, the two-sample z-test, and the two-sample z-interval. Let me be really clear. Anybody listening? You will rarely ever use these. Rarely. In order for me to use a z-test of any type, I have to know the population standard deviation. You should write that down. In order to use a z-test versus the t-test, I have to know the population standard deviation, which we call sigma. That's the O with tail on it. Right? So these z-tests, z-intervals, two-sample z-tests, two-sample z-intervals are different from the one prop z-test. Notice the word proportion is missing. The word proportion indicates categorical data. The z-test, if you look up in your calculator, you'll find that the values here, the functions I've given you, these are separate. You have a z-test, you have a one prop z-test. They're different. The z-test is quantitative, and it's kind of the perfect situation. If I know the population standard deviation, which is most likely you don't, so I'm rarely ever going to use those four tests or intervals. On the other hand, the t-test, the t-interval, the two-sample t-test, and the two-sample t-interval are exactly like the one prop z-test, two prop z-tests, and intervals, right? They're exactly the same. It's just that they're quantitative. And so we'll use those when we get to quantitative things. And it is a single test for a single sample, for two samples, and then, of course, the intervals that go along with them. TCDF and inverse T are exactly like you think they are. And TCDF is just like normal CDF, and inverse norm is just like inverse T. However, a little bit about those things. When I use TCDF and inverse T, with the normal CDF and inverse norm, when I use these two values, I kind of had a lot of freedom in how I could put stuff into it. With the T distribution, I'm very limited on how it works. When you use TCDF, it must be T-scores. So lower value and upper value have to be like the Z-score like it was before. In this case, it's going to be your T-scores. You can't put in X values, right? And then, of course, you're going to use your degree of freedom. Remember, degree of freedom is just n minus 1. So at a sample size of 20, my degree of freedom is 19. Super easy. Okay? Again, this is going to give me the area or the probability of whatever event happening. Inverse T requires the percentile. I don't think they've updated the new calculators to have left, right, and center. If you do, then it works the same as before. I don't think it does. Maybe they updated it. So you'll have to put in percentile. Notice the picture I've got down at the bottom. I wrote this because the percentile of a distribution is always the area to the left. Always. right? And then when you do that degree, it's going to give you that t-score that marks off whatever area that is. So if you're looking for the top 5%, you'll have to use 95%. Top 10%, you have to use 0.9 in the inverse t. And that will always give you back the t-score. If I want the x value that marks that off, what we'll have to do is we'll have to go back up to the top and we'll have to plug all that stuff back into our t-score formula, and we'll have to find out what that x bar is. That's what we're looking at here. Questions? Okay. Assumptions and conditions. Good news, for the most part, there's not a lot of difference here. Okay, you got randomization, independence, 10%. These are identical to what you did before. This one is still called the large enough condition, just like before. But last time it was called success and failure because that's what we used. This time it's called nearly normal. Now, if you look on the screen, this is a little bit more complicated. There's 3 different situations you have to kind of keep up with. Number 1, small sample sizes. That means your sample is less than 15. Now, the t-distribution is very robust. It can handle even really small sample sizes as long as certain things are true, and that's what this is, right? If you have a very small sample size, we have to justify that it's unimodal and symmetric, at least for the most part, okay? With really small samples, that's kind of difficult to do. What we want to look at is we just want to make sure that it's not all skewed on one side, right? For medium sample sizes, that's between 15, including 15, and up to, but not including, 40. If it's between 15 and 40, if you make a sketch of it, and yes, we're going to have to make a sketch like a histogram and look at it, or use a normal probability plot. A sketch is required to justify this graph, this assumption. So when you check nearly normal, you have to make sure that you actually draw a picture of the graph you're using to show me that it's either straight or that it's got this nice symmetric histogram and you're good, or a little bit skewed. So between 15 and 40, you can have slight skewed graphs. They can be slightly skewed, but nothing major. If your sample size is greater than or equal to 40, it's a free pass. I don't have to provide a graph. I don't have to provide anything other than the fact that I can tell you my sample size is greater than 40, therefore I get to assume normality. That's your central limit theorem, and you're kicking in there, right? Doesn't matter what the shape is originally. If you're looking at sample means, then as long as my sample size is large enough, it's always going to generate that normal model. And if it's larger than 40, that's kind of my free pass, right? However, outliers are not ever allowed. Now, I don't mean just kind of a little bit away. I mean, if there's major outliers in play, that's a significant problem. That is going to cause issues because we know that means and standard deviations are non-resistant, right? It means that the outliers are going to cause big issues when you go to look at your normality and talk about probabilities, right? So it won't work out that way. Okay, here you can see this is your t-table. This is literally a photocopy of what's in your formula sheet. And so be careful. There's a couple of things that are a little different about this one versus the z-table. Number 1, if you look in the top, the tail probability, it's telling you that the tail probability written right here on the top row is representing this top area to the right. That's a greater than probability. So we have to be very careful. Now, we're probably not going to do a significance test in this order. We'll probably use our calculators to do that just like normal. But let's talk about the first thing. If I had a confidence level, let's say we had 90% confidence. then what's the critical T star for a sample size of 20, right? That means I have 19 degrees of freedom. I think we can figure this out. If you think about it, what I'm going to do, I'm going to go down to 19 degrees of freedom. So on the sides, your degree of freedom over here. So 19 is here. And then I'm going to go across to 90%. So we're going to kind of match those things up. So 19 degrees of freedom with 90 degrees of confidence, you have a T star of 1.729. Does that make sense?
Yeah, it does.
So when you're using the formula, and that formula was X bar plus or minus your critical T score with n minus 1 degrees of freedom times S over the square root of n. Now remember, some of the harder multiple choice questions require you to be able to manipulate this equation. Knowing that margin of error is certain parts, standard error is certain parts. It will require me to be able to use this table. When I'm using the T-score or T-interval, I won't need to do this. It'll ask me for sample size, it'll ask me for the confidence level, and the calculator will automatically adjust automatically. You won't need to know it. You'll just type in the other parts. Now, sometimes you may get a T-score, and you may ask, what's the probability? What's my p-value for a certain T-score? So let's just say you had T is equal to, let's say it was 2.13, and your sample size, we'll say that's 20 again. And what if your null height, let's say your null was, your alternative, was mu is greater than, it doesn't matter, 5 or whatever. The question is, what's the probability for a situation like this? So I'm going to go down. I'm going to follow down to 19 degrees of freedom again. And what I'm looking for is 2.13. So so it's in between these two numbers, right? Here's 2.093, 2.205. So the question is, what's the probability? What's the area in the tail if I were to have that z-score? So I can't tell you exactly what it is, but I can tell you what it falls in between. So if I were to go up to the top, okay, 0.025 and 0.02. So if I had a t-score of this with 19 degrees of freedom and a greater than alternative, then I could tell you, well, my p-value is between 2.5 and 2%. With a traditional alpha level of 5%, either way, I'm going to reject the null in this case. Right? So it's not common that we do this, but that's how you would use this table. Does that make sense? It works backwards as well. If you know what your alpha level is, and you want to know what the t-score is for that alpha level at a certain degree of freedom, let's say I have 5% alpha, right? It's right here. And then I go down, let's say it's still 20, a sample of 20, my 19 degrees, right? That's at 17.29. If I get a t-score bigger than 1.729, I'm going to reject the null with an alpha level of 5%. If my t-score is less than 1.729, I'll filter reject it. All right, questions about that? Here we go. The scenario is, do college students get more than 7 hours of sleep a night? Right? 7 hours would be considered enough sleep, so they're using 7 as the baseline. And so what they did was they went and asked 25 college students, how many hours of sleep did you get the night before? And so they got a random sample of students from a certain college, and here's your response. So let's talk about what's different about my significance test screen. Okay, so first of all, when I bring up my t-test, I'm going to get some interesting things at the top. So input, data versus stats. So you got two different setups. This is data. If I gave you stats, it would say average, sample size, standard deviation, no data at all. Okay? It doesn't matter. Data is a little bit more work for you because it means you have to enter all of these things in to guess where? Your favorite L1. So all of our lists are now back. We're going to be working with that. So what I'd like for you to do, take about 2 minutes and put all those numbers in. You have 25, so make sure you get 25 numbers in, and then we'll come back and we'll kind of continue. Okay, once you've got all the information input into your L1, then you're ready to set up and do a significance test or a confidence interval, right? It doesn't matter. You can do either one. If I pull up the T interval, and this is true for the 2 sample versions, it will ask me the same sorts of information. Lists or statistics, data sets or statistics. And so the question was, do college students get 7 hours of sleep or not? So what is the null hypothesis for this kind of environment? Well, the question was, do they get more than 7? So my alternative is going to be greater than, so my null is going to be equal to 7, right? And so here you can see phantom. We're going to be doing phantom for our t-test. Our null hypothesis, HO, mu equals 7. HA, mu is, or maybe it's did they get inadequate sleep? The question was, I had the question backwards, is do college students get too few hours of sleep versus too many? So it's less than, so they claim that college students don't get enough sleep, right? Sorry, I had that backwards, which makes a lot more sense. Most college students are probably getting a lot less sleep than they need. Let's go through our assumptions and conditions. Okay? So to check our assumptions and the conditions, we're going to have to do a couple things. Number 1, randomization. This was stated in the problem. They chose a random sample of students. Okay? The hours of sleep from random students are definitely independent from each other. My 10%, well, I only chose 25 students, right? There's definitely more than 250 college students at any college. So I'm definitely well underneath the 10% rule. Nearly normal. Okay, let's talk about how to do nearly normal. This is also a calculator thing. Here we go. When you look at your nearly normal plot, so second y equals brings up your stat plots. When you open that up, you want to make sure you've got plot on. You want to make sure that you've either chosen the histogram or the normal probability plot. I tend to choose the normal probability plot because it's going to be really easy for all sizes of graphs, all sizes of samples. Like super, super small samples are very, very finicky when it comes to looking at your histogram. Based on how you set up your bins, I could set my bins up to make it be skewed or to be symmetric and not anything else. So I don't trust that as much. So that's why you see here, I've got a nearly normal is a normal probability plot. If this plot is linear, then it's approximately normal. If the histogram is nice and symmetrical, then that's good. Now, for this sample size, I can have a little bit of skewedness and still it be okay, right? Sample sizes of 25 allow for some skewedness. So if you had a slight curvature to this data set, you're still okay, right? And sometimes you might want to look at both of them, looking at the histogram or looking at the normal probability plot. That's that sixth icon. Can give you kind of maybe a more confidence that you're making the right decisions, right? So when you go through this, the rest of this, you already know how to do. I'm going to get a t-test. My t-score is going to be negative 1.674. My degree of freedom is 24, by the way. You're going to want to do that. Next to your t-score, put your degree of freedom in. This is one of those things that they don't always ask for, but when they do, it's nice that you've already got it. And then your p-value, and then next to your alpha level. In this case, our alpha level is not is smaller than my p-value. or my p-value is larger than my alpha level. So we failed to reject your null hypothesis because your p-value is greater than your alpha. We do not have enough evidence to say college students get less than 7 hours of sleep on average. Now, I could have said this, I could say we have good amount of evidence, but at the 5% alpha level, I don't quite have enough, right? If I had increased my sample size a little bit more, maybe gone with 50 students instead, that might have been enough to reduce the variation and reject the null. Okay,